In the previous lecture, we took an in-depth look at the monoclinic space groups. We looked at the diagrams of the monoclinic space groups, the naming convention, how to read the international tables. In this lecture, we're going to take a look at the space groups that belong to other crystal systems. We're going to see how the names are chosen for those space groups and also what the diagrams in the international tables look like. So when we think about the names of the various space groups, we're using really the same ethos that are used for point groups. I mean, in a point group like M3 bar M, there are many, many symmetry elements, but the name only contains 3 symmetry elements. And those 3 symmetry elements are all you need to generate all of the other symmetry elements. So we're going to do something very similar with the names of space groups. And because of that, the different symbols in a space group name refer to different directions in the unit cell. So we looked last time at the monoclinic case. And in the monoclinic case, like P2 sub 1 over C, the twofold axis, if it's present, or the 2 sub 1 screw, has to be along the B axis. And if there's a mirror or glide plane, it has to be perpendicular to it. The other one that's pretty straightforward would be orthorhombic. And we did finish the last lecture with an orthorhombic example. And in that case, all orthorhombic space groups contain first a letter that tells us about the centering, P for primitive, F for face-centered, I for body-centered, and usually C for base-centered, but sometimes we might see A or B. Those are just different variations of base-centered. So that's what the first letter is going to tell us. And then the next 3 symbols tell us about the symmetry about the A, B, and C axes. Okay? And if it's a 2 or a 2 sub 1, it's telling us that that rotation axis is parallel to the A, B, or C direction. And if it's some kind of mirror or glide, it tells us that that plane is perpendicular to this direction. So PNMA tells us that we have a primitive orthorhombic space group with an N glide perpendicular to A, an M glide perpendicular to B, and an A glide perpendicular to C. The next 3, tetragonal, trigonal, and hexagonal. In all of those, right after the letter that tells us about the centering, we are going to see a symbol for the highest order rotation axis. We'll have some kind of 4-fold axis, might be a screw axis or a rotoinversion axis, but some kind of 4-fold axis for a tetragonal space group, some kind of 3-fold axis for a trigonal space group, and then some kind of 6-fold axis for a hexagonal space group. But we don't have different letters for the A, B, and C. In a tetragonal space group, there's a 4-fold rotation. So that means whatever symmetry is associated with the A axis must also be associated with the B axis. So in all 3 of these space groups, the symbol that's in what I will call the second position tells us about the symmetry about the A and the B axis. Because due to the symmetry of these space groups, that symmetry element will always be the same. And then the third position for the tetragonal, trigonal, and hexagonal space groups tells us about another direction that's not parallel or perpendicular to any of the axes necessarily. We'll see those later when we look at diagrams. And then finally, when we come to the cubic space groups, after the letter that gives us the lattice centering, the first position we have the symmetry element that is for an axis would be parallel to A, B, and C, or for a plane, a mirror or glide plane, it would be perpendicular to A, B, and C. The second position always contains a 3 or a 3 bar, because that second position is going to be along the body diagonals. And remember, the defining symmetry element of a cubic space group is 3-fold axes along the body diagonals. And then finally, the third position would be along the face diagonal. In the slides that follow, we're going to graphically look at those, and I think it'll be a little bit easier to see it there. All right, let's look first at the orthorhombic, maybe the most straightforward one we're going to see in this lecture. This is the diagram for the orthorhombic space group PNMA. Okay, and that's the short name. The long name of this space group is P 2 sub 1 over N, 2 sub 1 over M, 2 sub 1 over A. Okay, and in the conventions that's used for orthorhombic space groups, if we have a rotation axis or screw axis and a perpendicular mirror or glide plane, in the short symbol we just write the mirror or the glide plane. If we see this first position here, that is the symmetry associated with the A axis. We see we have a 2 sub 1 screw and a parallel N glide. Where are those things going to be? If we wanted to see the 2 sub 1 screw, we should probably look in this drawing here. This is looking down the A axis. And you can see here are the 2 sub 1 screws. If you look at these diagrams, you're going to see that in every projection we see a 2 sub 1 screw coming out at us. And that's because there are 2 sub 1 screws running in all three directions. But what about the N glide plane? Where is the N glide? Well, it's going to be perpendicular to A, and so here we see a glide plane perpendicular to A. And in this drawing, which shows the projection in the AC plane, here is that same glide plane also perpendicular to A. The dash dot symbol means it's an N glide. And then finally, in this diagram, which is the projection in the BC plane, we see that the glide is across the diagonal of this face of the unit cell. Right? So the glide is half C plus half B. That is an N glide, and it's perpendicular to the A axis. Then for the second position, we see that there's a mirror plane perpendicular to B. Remember that the symbol for a mirror plane is just a solid line. So we see here is the mirror plane in the AB projection, perpendicular to the B axis. Here it is in the BC projection, perpendicular, as it must be, also to the B axis. And then in the AC projection, of course, the mirror plane is in the plane of that projection. And this symbol up here is what we see for a mirror plane, is a 1/4 of the unit cell above the base of the unit cell in the AC plane. Finally, in the C direction, we have an A glide perpendicular to the 2 sub 1 screw. Where is that A glide? Okay, here's the AC projection, and so you can see this is a glide plane that is perpendicular to C. It's an A glide because when we have the dashed line, it means that the translation part of the glide is in the plane of the projection, that is, in the A direction. Here we see also a glide plane perpendicular to C. The dotted line tells us that the translation is coming out at us, right? Which is, in this projection, the A direction. And then finally in the AB plane, this is a glide that's perpendicular to C. So this glide plane is in the plane of the projection, and the translation you can see is pointing in the A direction. All right, so this is how we would look at the drawings for an orthorhombic space group. What about the tetragonal case? Okay, let's look at an example of tetragonal. All tetragonal space groups are going to have some kind of fourfold axis that's going to be parallel to C. And the projection we see in the international tables is always the projection into the AB plane. So we're always going to look at these and see, okay, there's a fourfold somewhere. In this particular space group, it is a 4 sub 1 screw. And so we see here are the 4 sub 1 screws on the centers of the edges. We don't see any symbolism up here that would say that there's a mirror or a glide perpendicular. So we just write P 4 sub 1. If there were a perpendicular mirror, it would be /M. So it would be P 4 sub 1 over M. But there is no perpendicular mirror here. Then we look at the second symmetry position, and that's telling us in a tetragonal space group, that tells us about the symmetry that is parallel to the A and B axes. And so we see there should be a 2 sub 1 screw. Where is that 2 sub 1 screw? You can see here in red, this half arrow, that's the symbol for a 2 sub 1 screw that is in the plane of the projection. So we see that these 2 sub 1 screws are running parallel to A and parallel to B. And then finally, for a tetragonal case, the third position isn't the symmetry in B, because as we've already said, that's the same as in A. Instead, it's going to be the symmetry along the face diagonal, right, along these directions. And along these directions, you can see we have a twofold rotation axis. That full arrow is the symbol for a twofold rotation axis that is in the plane of the projection. Okay, so this is space group P, 4 sub 1, 2 sub 1, 2. When we look at the trigonal and hexagonal cases, they're the same. The only difference is in a hexagonal case, we're going to have a 6-fold rotation axis, whereas in a trigonal case, the highest rotation axis is going to be a 3-fold. In both cases, the axis is going to be parallel to the C axis. So, like the tetragonal case, the only drawing we see in the international tables will be the projection in the AB plane. And you can see the triangles in all of these drawings. Right? So these all have 3-fold rotation axes. Here I'm showing the images for 4 different trigonal space groups. But what's a little bit trickier is then the symbols that come in the second and the third position. All right, for trigonal hexagonal, this red symbol here that comes in the second position, here it's a 2, that would be the symmetry elements associated with the A and the B axes. And they always have to be the same. So here it's telling us, all right, we have a 2-fold rotation axis that is parallel to A and to B. Where is it? Well, here's our 2-fold rotation axis parallel to A, and there's our 2-fold rotation axis parallel to B. And then we finish with a 1. Sometimes this is not written, but for trigonal space groups, usually it is. That would be the symmetry that would be perpendicular to the A and B axes. Since it's a 1, there is no symmetry. So that's it. If we look at the lower right, we have a very similar space group, but here the symmetry element that is in the second position is a mirror plane instead of a 2-fold. So where are the mirror planes? Right, so these are going to be planes that are perpendicular to the A and B directions. And here they are. These vertical mirror planes are perpendicular to A. These mirror planes here are perpendicular to B. And both for the 2-fold rotations and the mirror planes, we have, a third one that's not perpendicular to A or B. Because of the 3-fold rotation axis, we have to have mirror planes that are at 120-degree angles to each other. And as it turns out, actually, this is oftentimes the easiest thing to look for. So if you have a mirror that is going to be in the second position here, then we look for it along the long body diagonal. Okay, now what would happen if we were to move that 2-fold axis, or that mirror, to the third position? So that's what we see on the left-hand side of this page. Now, because there's a 1 in the second position, there is no rotation axis parallel to A or B. Instead, we see it's in the third position. So that means it's going to be perpendicular to A, as we see for that 2-fold rotation axis, or rotation axes, I should say, or perpendicular to B. And that's what we see with those 2-fold rotation axes. In both of these space groups, we have a 3-fold rotation axis, and then we have perpendicular 2-folds. But it's just the orientation of the 2-folds is different here and here, and that leads to a different space group symmetry. If we were to put the mirror plane in the third position, now that tells us, okay, the mirror should be perpendicular to these 2-fold axes here. So since the 2-fold axes are perpendicular to A and B, it means the mirrors are going to be along A and B. And so there are our mirror planes. There's a mirror plane coincident with the A-axis, a mirror plane coincident with the B-axis, and then this third one along the short diagonal of the unit cell, which is at a 120-degree angle from the other two. It's a little tricky, kind of easy to make a mistake that, you see these lines here that are thin lines. Those are not mirrors. Those are just telling us about the unit cell. And here, the somewhat thicker lines, though, those are mirror planes. So this is the convention that we use both for trigonal and hexagonal space groups. And then finally, when we come to the cubic case, which has a lot of symmetry elements, and they're kind of at angles that make them not so easy to see, we start, as we do with all of these, with a letter that tells us about the centering or lack thereof of the Bravais lattice. This P432 is a primitive cubic lattice. The next symbol would tell us about the symmetry elements that are along the A, B, and C directions. Here it tells us that we have a fourfold, and you can see there's our fourfold rotation axis that's parallel to C. Here and here we see the fourfold axes that are parallel to A and B. Then we go to the second position, and we see for a cubic space group always a 3, or maybe a 3 bar. And that is the symmetry element along the body diagonals. That's why it has to be a 3 if it's a cube. And here we see the representation of the body diagonal threefold rotation axes. And then finally, the third position is a lot like it is in the tetragonal case. It's going to be along the face diagonals. All right, so here we see that we have a twofold rotation axis that runs along this diagonal of the AB face and along this diagonal of the AB face. And not just the AB face, it would be all the faces of the cube. So that's the symbolism used for a cubic space group. Okay, this is a diagram from one of the space groups, one of the 233-dimensional space groups, and I would like you to look at this and figure out what is the name of this space group. What is its point group? What is its crystal system? And one thing that's not easy to tell from the diagrams oftentimes is the centering. So in this case, we have a primitive lattice. Why don't you pause the video, take your time, and see if you can make a prediction, then come back and we'll go through the answer. Well, what'd you get? Can you see the fourfold rotations? Actually, there are 4/2 screws. Right? I would think that's the first thing that comes to my mind. We're looking for generally the highest order rotation axis, because that's going to tell us what sort of space group we have, and that allow us to better interpret the diagrams. And I don't see any sign of a threefold axis. I know now I've got a tetragonal space group. And I also know that I'm looking at the AB projection. What are the other symmetry elements that we see? We also have a twofold axis. That's in the same direction as the 4/2 screw axis. So it is a symmetry element of this space group, but it's not going to show up in the name. But now, for a tetragonal space group, the next thing we want to look for are the symmetry elements that are associated with the A and B directions. And what we see is, in those directions, we have this dotted line, which is a glide plane. And the dotted line tells us that the glide is coming out at us from the plane of the projection. And the direction out at us is the C direction. So that is a C glide plane. And we have it both vertically and horizontally. Now the last or third symbol in a tetragonal space group is going to be the symmetry that is along the face diagonal. And so here you can see that along the face diagonals we have mirror planes. Okay, so now we've identified all of the symmetry elements we need to name this space group. And the name is going to be P 4/2 CM. We can get the point group by turning the screw axes into rotation axes and the glides into mirrors. So the point group here is 4mm. And then finally, the crystal system, as we've already identified, is tetragonal. Okay, so that's how you might look at a diagram and figure out what is the name of the space group. Let's look at the name of a space group, the short Hermann-Magwin name, and then from that determine the crystal system Bravais lattice and point group. All right, so the first one here, PMMA, why don't you see if you can do these two. Pause the video, and then we'll go through them. Okay, PMMA. Well, we don't see any higher order rotation axes. We don't see a 3 or a 4 or a 6. So that rules out a lot. We can rule out cubic, hexagonal, trigonal, and tetragonal. So that tells us, all right, the only ones left are monoclinic, triclinic, and orthorhombic. But the fact that we have mirrors in more than one direction tells us it must be orthorhombic. So this is an orthorhombic space group. The point group is MMM, right? We're going to turn this A glide into an M. And it is a primitive Bravais lattice, primitive orthorhombic because of the P. And the presence of a glide plane in the name tells us that this is a non-symmorphic space group. Now, the second one, I4 sub 1 over A, what did you get for that? Well, we see that 4 sub 1. And there's only two kinds of space group that have a 4 in the second position, either tetragonal or cubic. But in the cubic case, the 4 has to be followed by a 3. So we can rule that out. This is a tetragonal space group. Because there's an I, we can identify it as being a body-centered tetragonal Bravais lattice. And then the point group is, once again, the 4 sub 1 screw becomes a 4-fold. The A glide becomes a mirror. This is point group 4 over M. And because we have both a screw axis and a glide in the name, this is another non-symmorphic space group. Well, let's do a couple more. Once again, I'll give you just a second for you to make these predictions, and then I'll reveal the answers. Okay, what did you get for the top one? Well, once again, I'm seeing only mirrors and two-folds. And if I'm only getting mirrors and two-fold rotations, then it's either going to be monoclinic or orthorhombic. But in the monoclinic case, there can only be one mirror, and it must be perpendicular to the two-fold. So this is an orthorhombic crystal system. The I tells us that it's a body-centered orthorhombic space group. And the point group is MM2, which sometimes we'll write as 2MM. This is another non-symmorphic space group. And then finally, this last example, I23, when you look at that and see the three-fold rotation axis, it might make you think that this is a trigonal space group. But for a trigonal space group, the three-fold is going to come in the first position after the centering letter. The fact that it comes in the second position tells us this is a cubic space group, albeit one that doesn't have a fourfold. So this is a body-centered cubic space group, right? Crystal system cubic, Bravais lattice body-centered cubic. The point group is 2, 3, and because there are no screw axes or glide planes here, it is a symmorphic space group. One thing I'll say about the distinction between symmorphic and non-symmorphic space groups is that you do sometimes encounter symmorphic space groups that have a screw axis or a glide plane, but it never shows up in the name, right? So those things only exist because of the closure rule and the synergy between the other symmetry elements that are in the name. One last thing I want to touch on before we end this lecture, and that is, how do we choose the origin? In fact, it's not up to you to choose the origin. That is generally done for you in the international tables. But the convention that's used to fix the origin would be as follows. If we have a symmorphic space group, like P6MM, then we're going to always place the origin at the invariant point of the point group. What do I mean by that? Well, if we have a point group, there's always got to be one point that is not changed by the symmetry operations of the point group. And that's going to be where the rotation axes and the glide planes intersect. Sometimes there might be an inversion center at that point. Here, it's where the sixfold rotation axis intersects with the mirror planes. Now, when we look at non-symmorphic space groups, there is no such point. Here in P2 sub 1 over C, which is non-symmorphic, here's our 2 sub 1 screw. Our C glide is 1/4 of the way above this projection. Here's an inversion center, which doesn't sit either on the 2 sub 1 screw or on the glide. In those cases, we pick the point of highest symmetry, and when possible, we will typically pick the inversion center to be the origin. You will find a variety of space groups for which there are two different choices of origin. And you'll see that when you're looking through the international tables. You just want to be a little bit cautious that if you are using the coordinates that go with, for example, setting 1, where we put the inversion center maybe where different rotation axes intersect, but really those coordinates go with origin choice 2, which might be, let's say, at the inversion center, that can confuse you. So just be aware that many space groups, or at least some of the space groups, have multiple choices of origin that are equally valid, and you'll find both of them in the international tables.